Hello, and welcome to the lecture on 4.3. Today we're going to talk about logarithmic functions. So first what we need to do is recall f inverse of y is equal to x if and only if f of x is equal to y. Now the reason we need to recall this is because a logarithmic function is actually going to be defined as the inverse function of an exponential. And also recall that an exponential looks like this. Let's start with the definition. Let a be a positive number where a is not equal to 1. The logarithmic function with base a, denoted by log a, where a is a subscript, is defined by log sub a of x is equal to y if and only if a to the y is equal to x. So remember what I was saying just a few minutes ago about how a logarithmic function is the inverse function of an exponential. That's what we're saying here. So if a to the y is equal to x, then the logarithmic undoes this rule. And we'll get more into this in a second. Note, log base a of x is the exponent to which base a must be raised to get x. Remember, log base a of x is equal to y if and only if a to the y equals x. So here what we're saying is a to this power gives us this. So log base a of x is the exponent to which base a must be raised to get x. Log base a of x is this exponent. It's equal to y, and y is right here as an exponent. So a needs to be raised to this exponent to give us x. Note, the logarithmic form log base a of x equals y is interchangeable with the exponential form a to the y equals x. Now, these two are actually interchangeable. They're saying the exact same thing. They're just saying them in different ways. So you can go from this form to this form by just pattern matching. And I'll show an example of this. Find the following values. A, log base 3 of 81. And B, log base 2 of 256. Remember, log base a of x equals y if and only if a to the y equals x. So we pattern match here. In this case, in part A, our base is 3. So our a is 3. Our x is 81. So this is interchangeable with this. 3 to what value? I'm changing it to this form. 3 to what value equals x? And remember, our x is 81. So 3 to what value gives me 81? What exponent do I need to apply to 3 in order to get 81? That exponent is 4. And we can rewrite this as 3 to the y equals 3 to the 4th. And since an exponential is a one-to-one function, it's always increasing. 3 to the y equals 3 to the 4th means y is equal to 4. Now this means that we can say log base 3 of 81 is equal to 4. Now, remember the statement I made before. This logarithm means 3 to this power gives me this value. 3 to this power gives me this value. Let's try this one. And you should try this one on your own for a second and then come back and see if you got it right. So we're going to rewrite this as 2 to some power y is giving us 256. And then we just have to figure out what power that is. 2 to the y is equal to 2 to the 8th, which implies then that y is equal to 8. Means I can write it as log base 2 of 256 is equal to 8. Now I want you to try one. Find log base 6 of 216. Now we're going to list some properties of logarithms. Some of these properties should be relatively obvious. Other ones will be a little bit less intuitive. 1. Log base a of 1 equals 0. This should make sense. Now, it might not make sense immediately, but once you start to understand logarithms a little bit better, this should make a lot more sense. So remember, we're taking this base, we apply this as an exponent to this base a, so a to this power gives me 1. So ask yourself, if you have a positive base a, and you apply an exponent to that base, what exponent do you need to apply in order to get 1? Basically, a to what power gives me 1? And that power should always be 0. So here, log base a of 1 is always equal to 0. Now, again, we're assuming that a is a positive base and a is not equal to 1 for these properties, just like we assumed that here. This exact same assumption applies. Let a be a positive number where a is not equal to 1. 2. Log base a of a is equal to 1. This should also be intuitive. What power do I need to apply to a in order to get a to the first power? Basically, in another way of stating this is a to what power is equal to a? That power is 1. This is an understood 1 here as an exponent. So a to what power gives me a to the first power? 1. That should be pretty obvious. And again, it might not be immediately obvious because you're just learning about logarithms, but as you come to understand logarithms a little bit more, this should make a lot more sense. A similar rule here, a to what power gives me a to the x power? That's x. A to the x power is equal to a to the x. Another way of stating this is a to what power gives me a to the x. Basically, a to some power here gives me a to the x. Well, since a to the x is here, we're looking for a power to apply to a in order to get a to the x. It obviously has to be the x power. You have the same base. And 4, this one's a little bit less obvious. A to the log base a of x is equal to x. Now this one's a bit trickier. But what I want to state here is that these two properties are f of f inverse of x is equal to x, and f inverse of f of x is equal to x. These two properties here, one is taking the exponential function a to the x and composing it with its inverse, and the other is taking the logarithm, log base a of x, and composing it with its inverse. Now, since they're inverses of each other, these two are going to look a little bit similar. A to the log base a of x is equal to x. Let's peel this one apart. What I'm going to do is I'm going to take this exponent and I'm going to write it over here. Log base a of x is equal to y. I don't know what y is, but in the end it won't matter. I just want to set it equal to something so that we can see. So remember what this means. A to this power gives me x. So I can rewrite this as a to the y power is equal to x. So here I'm saying that log base a of x is equal to y. I've set this equal to y. I don't know what y is, but I don't care. In the end, it will not matter. The fact is that I set it equal to y, and this statement is the same as this statement. It's just a different form. But since log base a of x is equal to y, I can replace log base a of x with y. Now suppose I'm looking for what this is equal to. I don't know. I might not know what this is immediately. But remember, log base a of x is equal to y is the same exact statement as a to the y is equal to x. Now what do I have here? A to the y. So it has to be x, which is where we get this x here. As I said before, that y doesn't matter. It's kind of a dummy variable when looking into this. Now, again, as you come to understand logarithms a little bit better, hopefully this makes a little bit more sense. It helps to think of a logarithm as an exponent. And when we get to the log rules in the coming sections, that will help a lot more. Example. So find the following values. Log base 300 of 1. B. Log base 5 of 5 to the third. And C. 6 to the log base 6 of 30. This one's pretty straightforward. It's the exact first property. Also, 300. We're saying 300 to what power gives me 1? That's 0. This is definitely equal to 0. Log base 5 of 5 to the third. So 5 to what power gives me 5 to the third power? That should be 3. 5 to the third power gives me 5 to the third power. And then finally, this one is exactly the fourth property. A, in our case, A is 6. The log base A of x is going to equal x. So 6 to the log base 6 of x, in our case 30, is going to equal 30. All right, the next section I want to talk about is the graph of logarithmic functions. Recall. Remember what the graph of an exponential looks like. So we have this as our axes, cross at 0, 1, and it goes up like this. Let's call this y equals a to the x. Now this is important because, as I stated before, a logarithm is the inverse function of an exponential. So note, f of x equals a to the x means that f inverse of x is equal to log base a of x. So how do we figure out the graph then? Well, it's actually not as hard as you might expect. You might remember how to find the inverse of a graph. Let's say that we have our exponential graph here. Now, if you remember how to find the graph of an inverse function, you reflected about the line y equals x. So if we just reflect this graph, call it y equals a to the x. If we just reflect this graph about the line y equals x, then we have the logarithmic graph. So here at 0, 1 will become 1, 0. So we end up with something that looks like this. This will be the reflection over the line y equals x. Thus, this would be y is equal to log base a of x, because log base a of x is the inverse function of a to the x. So also recall, for the function f of x is equal to a to the x, the domain is all real numbers, so negative infinity to infinity. And the range is 0 to infinity. Now, remember also that when we find the inverse of a function, we essentially interchange our x's and y's. So we actually interchange our range and domain as well, because now everything that could have been a y value becomes everything that could be an x value. And then everything that could have been an x value becomes everything that could be a y value. So, for the function, f of x is equal to log base a of x, we have a domain, 0 to infinity, excluding 0, and a range of all real numbers. Right. Now, this is important because previously, when we talk about domains and how to find a domain, we were always looking for x values that cannot exist in that particular function. So for instance, like a rational function, anything that makes the denominator equal to 0 is not in the domain. And when we have a radical function, like for instance, f of x is equal to the square root of x, we can't have negative numbers under an even radical. Well, here we see that our domain is from 0 to infinity. So we actually, if I was trying to find the domain of a function, for instance, this example here, find the domain of f of x is equal to log base 2 of x plus 1. What would the domain be? Well, notice that our logarithms cannot take a 0 or negative numbers. The domain of log base a of x is all positive real numbers and only positive real numbers. So everything that goes in here has to be a positive real number. So we say that then that x plus 1 has to be strictly greater than 0, which means then that x is strictly greater than negative 1. So we end up with this. This would be our domain. Now, what if we had something that looks like this instead? Now, this one's a bit trickier. It's the same idea. We do the exact same thing. 2 minus x is greater than 0, and we solve for x. So x is less than 2. Now, this means that x can be any negative number. Is that possible? It is, for this particular function. Because remember, let's say that x is negative 1. Whatever goes in the input for a logarithm has to be positive. So if x is equal to negative 1, we would have 2 minus negative 1, which is 3. If x is negative 10, 2 minus negative 10, which is 12. So noting that this negative here is causing us to be able to put in negative numbers for x. Now, if x is equal to 3, which as we can see is outside the domain, we would end up with 2 minus 3, which is negative 1. Of course, logarithms cannot take a negative number, so this would be undefined. So you have to be careful with domains a bit. I want to talk about graph shifting for a second. Graph shifting, as we know it, will apply to logarithmic functions just like they did with exponential functions. Graph shifting and stretching and shrinking. So if I were to say graph the function f of x is equal to log base 2 of x minus 3. Notice that this negative 3 is directly affecting the x, so it's going to shift to the right 3 units. Now remember, in an exponential function, we have a horizontal asymptote. So for a logarithmic function, we have a vertical asymptote. This would be our vertical asymptote at x equals 0, or just log base a of x. But here, we're shifting 3 units to the right. So we need to shift our vertical asymptote 3 units. 1, 2, 3. So this becomes now x is equal to 3. This is our vertical asymptote for this particular log function. And then to graph it, we graph it just like any other log. Right? We move all of the points that were over here to over here now. We would end up crossing at 4, 0. And we get something like this. All the other shifting and stretching techniques are the same as well. So for instance, f of x equaling 3 log base 2 of x will vertically shift the graph by a factor of 3. Go ahead and try one. Graph the function f of x is equal to log base 3 of x plus 1 minus 2. The next thing I want to talk about is common logarithms. The logarithm with base 10 is called the common logarithm and is denoted by omitting the base. So it'll look like this, log of x, where it doesn't actually show a base. And this is the same thing as log base 10 of x. Now this is important because log x is on your calculator. That's a log base 10. The natural log is also on your calculator. Now the natural logarithm is just base e instead. The logarithm with base e is called the natural logarithm and is denoted by ln. So if you see ln of x, this is the same thing as log base e of x, where e is 2.7182818284598, so on. It's the number that we were talking about last section. Now, the natural log is a log just like anything else. It just has a special base, and the base is e. So recall, log base a of 1 is equal to 0. These were the properties of logarithms. Log base a of a is equal to 1. Log base a of a to the x is equal to x. And a to the log base a of x is equal to x. So these were the properties of the logarithms that we talked about before. All of these properties apply to the natural log as well. So ln of 1 is equal to 0 because it's just a logarithm. It just is base e, that's all. Ln of e is equal to 1 because it's the base. Ln of e to the x is equal to x. Again, e is the base. And e to the ln of x is equal to x. So as an example here, find ln of 1 over e to the third power. This is just -3 because e is the base of this logarithm. E to the -3 is equal to 1 over e to the third. All right, I'm going to do one more example. Find the domain of ln of -x squared minus 2x plus 15. Now remember, logarithms can only take positive values. So if we're looking for the domain of this, then we need to figure out when this interior part is positive, strictly positive. So we need to factor this. -x squared minus 2x plus 15. Now in order to factor this, I'm going to factor a negative out, and then we'll deal with that in a bit. This is the same thing as -1, x squared plus 2x minus 15. And we're looking for two numbers that multiply to -15 and add to 2. That's going to be 5 and -3. So this will factor then into -1 times x plus 5 times x minus 3. Now what I'm going to do is I'm going to take this -1 and I'm going to distribute it into one of these. Not both. It does not distribute into both. It's multiplying on the outside of both. If you distribute it into this one, then it's just gone. Or if we distribute it into this one, it's just gone. You can distribute it into the second one because it has a subtraction. So this will end up being x plus 5 times 3 minus x, like that. Now if you multiply this out, you should get this. Now again, we're looking for the domain of this. So we need to figure out where this function, which is the same thing as x plus 5 times 3 minus x, we need to figure out where this function is strictly positive. So let's figure out where it's equal to 0 first. Happens to be at 3 and -5. Then we build our chart and label. So here we have that x is less than -5, x is between -5 and 3, and x is greater than 3. We list our factors over here, x plus 5 and 3 minus x. and then our entire product, which is x plus 5 times 3 minus x. Now, again, we're looking for where this function is greater than 0. So let's write that here. And we're looking for where this is greater than 0 because logarithms can only take positive values, and we need to figure out what the domain is. So if x is less than negative 5, say negative 10, we would have a negative value and a positive value. So this product then is negative because we'd have a negative times a positive. If we're between negative 5 and 3, say 0, we have a positive and a positive. So we would have a positive times a positive. And if we're to the right of 3, say 20, 20 plus 5 is positive, and 3 minus 20 is negative. So we'd have a positive times a negative, which gives us a negative. So the only values for which this function is greater than 0 is between negative 5 and 3, where we exclude negative 5 and 3 because the logarithm cannot take 0 either. They have to be strictly positive numbers. All right, that's going to be it for today. I will see you all at the next lecture.